안녕하세요.
Hey, hello everyone. Welcome to our second ACM seminar. So I'm so delighted to have Professor Hong from SungKyunKwan University today, and he will be talking about recent advancements of scientific computing in deep learning. Let's give a warm applause to Professor Hong, and yeah, please.
Thank you. Can I take off my mask or?
Yeah, sure. I think you can take off your mask, right?
Is it
Anyone
okay?
knows the policy? Yes.
Okay, yeah. Okay, thanks for the invitation. Today I'm going to talk about the recent advancements of the scientific computing in deep learning. The title is very ambitious, the recent advancements, but it's recent advancements for me, not for everybody. So I just introduced my recent research to you, and if you have any question, you can interrupt me whenever you want. Okay. So everybody knows the great success about the deep learning and AI and machine learning and everything. We have a very nice example for the AlphaGo and speech recognition and face recognition and many applications out there. But as an applied mathematician, I have to ask a question to myself. First of all, well, okay, deep learning is very successful. Machine learning is very successful. But how can I apply the mathematical algorithm to the machine learning? That could be the first question to me. And second question is, how can I apply the machine learning algorithm or process to my mathematical problem? So those two questions just came to me when I start my study deep learning in 2017 or 18. So when I was in postdoc, it's kind of big wave to me, like the AlphaGo and that kind of the very interesting example. So at the time, I was just a numerical PDE guy. So I'm kind of a numerical analysis person. And I started to study deep learning and machine learning by myself. And then I have interacted with some of the outside of department, like computer scientists and engineers. And I found that it's very interesting. So I'm going to briefly introduce what is my interest in this direction. Okay. So those are the current research interests, like 5 or 6 different research interests. But today I'm going to focus on just 2 of them, like the security of AI, so-called adversarial attack and defense. And second one is optimal device design via deep generative models. So first one is the security of AI. So that part is I'm going to apply my mathematical algorithm to the computer vision problem. So this is the very interesting picture. So everybody knows deep learning is very powerful, but is this perfect procedure? Unfortunately, it's not. So here is one of the striking example. So that is called the adversarial attack. So here is a picture of the pig. So if we ask neural network, what is this picture? The neural network answer that it's 91% it's a pig picture. But if we introduce that kind of non-random, but very small noise, like epsilon is 10 to the negative 3-ish, that kind of small noise perturbation to the picture, and human eye, it's still nothing because we have a very small perturbation. So it's still pig picture. But if we ask the neural network, what is this picture? And neural network says it's 99% aligner. So we can fool the neural network by introducing unperceptive, that kind of non-random noise. So problem is, well, can we generate that kind of noise by ourselves? And how can we generate? And if we generate that kind of noise, how can we defend it? Because it's very important issue for the security of AI and safety of AI. Let me give an example. So when you drive, for example, in the US, so you're driving with autonomous car by using Tesla or whatever this is. The autonomous cars, and then you are driving and they take a picture many times. Every second they take a picture. And they take a picture like this kind of stop sign, then cars should be stopping. But if the little kids in the street, they just put some kind of the little sticker, which is very, very small stickers on the stop sign. And my car just take a picture of this stop sign, but there is just very small stickers around. And our neural network misunderstood this one is a yield sign. The pattern could be the adversarial attack. Then the car should just moving. And then the big accident occurs because the car didn't stop. So that is big issue for that kind of the autonomous cars and actual, safety of AI and security of AI. So there are many different examples like speech recognition and face recognition and spam filter, and you can find many different examples for that. And also we have a same problem for the adversarial attack for the voice recognition, but I have to turn on some kind of the voice for that, but I don't think that kind of the voice is working. Is that right? I can actually turn on your speaker so that it will work. Okay. So let me, okay. It's not working, I think. Probably I connected with I think you can turn on your okay. Okay. I will send a link in the YouTube. So 네. 알겠습니다. Okay. So where did this come from? So we have to understand what's going to happen about this kind of the adversarial attack. So that is very general process of the neural network. So we want to minimize the loss function. This theta is like the learnable parameter, and x is input, y is correct label. So x is big picture, and y is the correct label, and theta could be the parameter of our neural networks. And we are going to optimize this one by using the stochastic gradient descent or LBFGS, whatever this is, and find good appropriate theta. Okay, but for the adversarial example, we want to find maximize this loss value and x plus delta. So we can introduce tumor perturbation over our input picture, for instance, and then we want to say this delta could be small perturbation. So it's like a min-max kind of problem. So we want to minimize delta, but we want to maximize the loss value. So that means that means we can introduce that kind of delta, and then we can generate the adversarial example. But once we generate our adversarial example, then by using that kind of example, we can retrain our neural network. Then our neural network getting more robust. And we can also generate another adversarial example over that kind of the neural network once again. And then that could be another example for the adversarial attack. And then we can also retraining. We can just iteratively just going back and forth in that process. Then our neural network getting more and more robust. But there is a threshold. So we cannot make perfectly, well-designed neural network for that against this kind of the adversarial attack. So that means also we can understand that finding adversarial attack by using that kind of adversarial training, the attack could be the best defense. So finding attack, then by using that kind of example, we can retraining our neural network. That means best attack could be the best defense. So we want to study what is the best attack. then that could be automatically imply that we can find best defense for the adversary example. So what has been done so far? The computer scientists, they are smart, but they already studied that kind of example since 2014, maybe before than that, probably. So one of the famous attack method is FGSM. It's like the fast gradient sign method. If you understand the calculus, then you can understand what's going to happen. So J is your cost function, and gradient of J. That means, what's the meaning of the gradient of J? It's like the fastest change direction. So if you have a gradient of J and multiply by epsilon, and that means you are going to pick up the direction which is fastest change of your cost function, and you are going to attack in that direction to your input value. Then that could be the most inconvenient direction to your neural networks. So if you want to find this epsilon small enough, and then you can find that kind of direction together, and then you are going to attack your image, then that could be the kind of the strongest attack in that sense. So that is one of the methods for the FGSM. And the second method is BIM. It's like the iteratively doing that kind of FGSM. But for example, this epsilon is 10 to the -2, then that guy, our epsilon kind of alpha is 10 to the -3. Instead, we are going to attack 10 times. That means in the sports metaphor, it's like the big punch. Number one, epsilon is 10 to the -2, but this one is small jabs, like 10 times small jabs, 10 to the -3 attack, like the 10 different times, but changing the direction after attacking it. So which one is stronger attack? The second one. The second one turns out the stronger attack than the first one, because they just changing the direction, which is the most the uncomfortable direction to the neural network, and then we are going to japping to the neural network. So the second one is like the BIM or PGD. That's the same thing, actually. Depends on the initialization, but these are like the strongest attack for that kind of the problem. All right, so that is kind of the overview of the adversarial attack. But I'm a mathematician, so I want to do something for that kind of problem. So what can I do for that? So they just generate that kind of the attack. By using the attack, we are going to do adversarial training, but I said that's not enough, because accuracy for the CFAR10 for that kind of the adversarial attack is like the 50% accuracy for the even for the CFAR10. So what can I do? So before I start, some of them who are not familiar with the neural network, I'm going to introduce CNN and ResNet. CNN is, I think, it's like one of the neural network process, and the ResNet is CNN plus residual connection. So fx plus x, that is the ResNet architecture. So I'm going to use this kind of the ResNet architecture to tackle that kind of the problem. Mm-hmm.
In your previous slide, so how does the attack being defined? For example, if the delta, I think in the previous slide you mentioned about x plus yes. If the delta is, for example, y minus x, then actually that completely changed the image, for example.
Y minus y, actually you have a f of x is equal to y. So
right.
f of x plus delta is equal to y.
Right. So what I'm trying to say is, if x is the image of the dog,
mm-hmm.
if the delta is defined in a way that cat image minus dog, then by when you add x plus delta, then that's a cat image.
Oh, actually x is dog image, then delta is small perturbation. Like this. Like this.
Then how small it has to be somehow?
It depends. It depends on the problem. So normally we take this kind of the epsilon is like the 0.01, something like that. If this epsilon is large, then that is not adversarial attack, because it's not even cat picture, dog picture. It's distorted a lot. But if we introduce small perturbation, then human eye, we cannot find this is the attack or not. So that is the definition of the adversarial attack. So epsilon is small enough. And how small it is? Just small. Like the smaller than like the maybe 0.1, 0.01, something like that. Normally we put the 8/255 in the paper. That is like the universal, number of the 8/255.
Then how does the error noise level be defined in the pixel wise, like infinitesimal?
I think that is like error nonsense.
L1.
Yes, it's like the sign function, so it's like the error nonsense. Yeah.
Thank you.
Thanks for asking. Yeah. Okay, so now we know what is a ResNet. The ResNet is like the CNN plus itself, the residual connection. Okay, so that's all you need to know for that kind of subject. Okay, so I'm going to rewrite our ResNet architecture by using some kind of the dynamic system expression. It's well-known expression to some mathematical AI guides. So X is actually, X0 is like the input value, and this F is CNN, and X just our residual connection. So we have a L number of the layer, layer, and then the label Y hat is just our predicted number. So the predicted label. So I'm going to introduce, that's the exactly same as our ResNet architecture. So I'm going to introduce delta T is 1/L. L is the number of the layer. And I'm going to change this equation by introducing this funny f bar function. F bar is 1/delta T. Delta T here, so it's exactly same as before. Then, putting in that way, interestingly, it's very much familiar to all of us. You're moving this guy on the left-hand side divided by delta T. What is that? That's explicit Euler scheme. So if L, the number of layer, large enough, normally large enough, we can put the more than 100 layer, we can do it. Then that could be converted to that kind of nonlinear dynamical system. So we can understand the ResNet architecture as an explicit Euler scheme for that kind of the neural networks. But explicit Euler, that's very much basic numerical scheme. Nobody using it in these days. People using the higher order numerical scheme. So that is the example for the higher order numerical scheme. It's like the generalized Runge-Kutta, higher order Runge-Kutta method. So if you take the numerical analysis, then you will learn what it is. Now, so we can use that kind of the higher order Runge-Kutta scheme for that kind of the problem. So we can replace explicit Euler, aka ResNet, by using that kind of the higher order Runge-Kutta. But another question is, any kind of Runge-Kutta method useful here? If I just using any random Runge-Kutta method and then change our architecture by using that kind of the higher order method, then is it working? Actually not. We have to pick up we have to choose right numerical method for this kind of problem. Why? Because if we raise the order of accuracy, then there is a price to pay. What is that? Stability. We lost numerical stability. So we have to keep the numerical stability, but we want to raise the order of the accuracy. Is there any that kind of thing in the numerical analysis? Yes, I think Professor Lee knows that kind of thing very well. So it's like the TBD, the time discretization. It's like the strong stability preserving property. So it's developing back in 1990 by Stanley Osher and Chiwangshu and Tony Chen. And afterwards, many of the numerical analysts using it for the Wino method and discontinuous Galerkin method, people using that kind of method very much. So the point of this method is that it's higher than numerical method, but stability, the CFR number, is same as comparable to the explicit Euler method. So we have a same CFR condition, and then we can raise the order of accuracy. So that is the good part for the numerical analysis. So we are going to take it in. So that's the example for the simple Euler method, and that's the third order SSP. Of course, the order is higher, so you cannot see that kind of the numerical error. Of course, this is higher than numerical methods. And also, if you use random RK method and SSP RK method, there is a difference between them. It's like famous example. The red one is TVD method, SSP method, and non-TVD method is black one. So obviously, non-TVD method produce high oscillation for that kind of the Burgers equation example. But the red one is TVD method, so it's kind of smoothing because the total variation is diminishing. So that's well-known thing. I didn't develop it. It's like out there in the numerical analysis. So my idea is, okay, so this is SSP Runge-Kutta, also Hund's method, the second order, and this is third order. So I'm going to use this one, and I'm going to replace explicit Euler resonant architecture by using that kind of SSP Runge-Kutta method. So take a look at this 1/2, 1/2, 1/2, and 3/4, 1/4, 2/3, that kind of coefficient, I'm going to directly using it to my architecture in this way. So that guy is plain resonant block, and then B is SSP2 block. So you can see 1/2, 1/2 right here. And this guy is SSP3 block. You can see 3/4, 1/4, 2/3, 1/3 here. So it's exactly in the replacement. And see what happened? Then this is the very easy MNIST example. So clean image, there is no perturbation. Then MNIST resonant is 99% accuracy. Of course, MNIST is very easy. But SSP2, SSP3, also 99%. And SSP adaptive is I'm going to adaptively choose that kind of the parameter, 2/3, 3/4 kind of parameter. And then I'm going to put this one as a learnable parameter and then also learn everything. So that's adaptive method. So SSP kind of SSP-like method, also same accuracy for the clean example. But after taking FGSM attack, resonate its accuracy down to the 76%. But our SSP adaptive method is 85%. It's better. And PGD 20 means I'm going to japping 20 times. So I'm going to do the perturbation 20 times. That is PGD 20. So it's very strong attack. So resonant architecture is 57% going down accuracy, but it's still 67. So it's getting better. It's better. Yeah. And PGD30, actually PGD30, after doing PGD30, the picture is very much distorted. So it's not anymore adversarial attack example, but my reviewer want to do that kind of example, just play that kind of the example with that. Then our resonant, plain resonant, 17%, but still our SSP adaptive is 51% accuracy. So there is an improvement. And also we move to the CFAR10 RGB example. Then we have a clean CFAR10 is 85% accuracy. And we have FGSM attack, it's 52%, but it's like the 53% for the SSP block. So you think about it's very marginal difference, but actually in this community, this is not marginal. 1% difference in the averaging sense, it's very much different. So right now, I wrote this paper 2020. So right now, the number of around like the 59 or 60, there is an Olympic, like the raising that kind of accuracy by using the CFAR10 and then adversarial attack. And I just quit it because that kind of Olympic is not, I'm not interested anymore. And also it's kind of we need a lot of computing power and a lot of gradient students. So I just quit it. But at the time, it was kind of very good number. Yeah, I'm not sure that was SOTA, but I thought this is good number at the time. Yeah, and then this one is also similar, the example for the PGD7, 12, PGD20. So you can see that SSP-like method is always outperform the plain resonant because the region is this. That's one of region. So in the computer science, they have a name of the perturbation growth ratio, PGR. So I heard about the PGR and take a look at the equation. Then that's very familiar to us. What is that? It's just the local Lipschitz constant. So of course, our numerical method, TVD, so total variation diminishing. So our PGR, local Lipschitz constant, is smaller than plain resonant. So that's why this orange one is resonant PGR, and this green one is SSP PGR. So our SSP PGR is smaller than plain resonant. That is one of the mathematical evidence, not mathematical evidence, experimental evidence, why the SSP-like method works well for that kind of adversarial attack example. So yeah, I think I enjoyed this kind of the problem a lot. And then immediately I move on to my interest to the the video classification. So video is like the stack of the frames. So image is just only one frame, but video is like we can think about the 64 different frames. It's like the spatial temporal discretization of that kind of the image example. So, but this example, we don't see many of like papers and studies about that kind of the adversarial attack over the video. One of the reasons is that computation time is very, very expensive. Computation cost is very, very expensive. So that part, we don't understand what is the nice attack. How can we define the adversarial attack for that kind of the video example? So we start define what is the attack, adversarial attack over the video. So we have, for example, 64 frames. Should we make an attack for each of the frames? Or should we make an attack by selecting some of the frames, like 16 out of 64, something like that? What is the best attack? What is the better attack? So that kind of questions are on to me. So we just try to define what is the efficient attack in this kind of the video example. So video classification, you can take a look at this kind of the UCF 101 data set in the YouTube. Yeah. So this is kind of the example of the video classification, action recognition. So for example, it's like the making up, clearly making up, and writing a keyboard, typing a keyboard, and playing instruments. And that kind of the very simple task, we are going to ask our neural network, what is the task? And then can you recognize the kind of action? That is the example for the video classification. Sure.
Probably I'm not very familiar with the video classification. For example, one video may contain different content. Like in the first part, there's some man swimming in the pool, and the later part, some woman actually walking in the street. So are we considering this kind of complicated example, or just a simple type? There's one video, one simple message like image classification?
Not this test example. I choose UCF 101 dataset and Kinetics 400. These are very clear labeling examples. But if you go out there and then take a look at the Instagram 65, it's like the 65 million videos from the Instagram. And then they don't, it's like unsupervised learning example. So you can challenge that kind of example. Which as far as I know, it's very complex. It's super expensive for the computation course and very difficult subject. Because even the action recognition, it's not perfect as far as I know. Yeah. So architecture is very much different from the CNN because we have a temporal direction. So you can think about the LSTM, like the convnet, and then LSTM and action. That's easiest to thinking. And then also 3D convolution all at once. Or thinking about the optical flow about this kind of the video, then using the convolution network and then thinking about that kind of the action. So these are like the dominating method for the video classification thing. But my question is, how can we choose what is the most vulnerable frames? So what kind of frames should I choose and then make an attack? What is the most efficient way in this case? For example, we have a 64 frames. I'm going to pick up 8. What is the most vulnerable frames? So it depends on the architecture. So if you want to see that kind of the R3D ResNet 3D block, then it's like the importance. I just take the gradient of that kind of our image, like the grad chem idea. So this gradient is pretty much uniform. It's not uniform though. We can pick up some of them, but it's not very powerful. But some of the architecture, we can clearly find this kind of most vulnerable frames. Then in this case, we can give an attack. These of the most vulnerable frames, then our attack is, as efficient as all frame attacks. So that kind of method we studied, and then we just working on that kind of the adversarial attack, not defense at this point. Then our method is like the all means the whole frame attack, like the 64 frame, we are making an attack. It's 24% accuracy. It's attack method. So going lower, it's good. Okay. So the method is like the 8-frame attack is 28%. It's like a little comparable, like 4% difference, but we only choose 8-frame out of 32. And also that guy is like the 16%, the attack, and then randomly chosen is like the 52%. So PGD is stronger, actually. So, of course, all frame attack is most efficient and the most smallest. But if you can pick up some sparse frames out of 32, and we can choose 8 frames, then that could be comparable attack. So that is another findings, that kind of the adversarial example of the video. So our ongoing project is I'm going to defense the kind of adversarial attack by using our SSP-like idea. Then, we can find some kind of the better defense because we understand which frame is most important right now. So we can defense by using that kind of idea, then that could be the efficient defense. So that is our next project.
Just a quick follow-up question. I think a similar idea might be applicable for image classification in the sense of like which pixel is most vulnerable.
Very interesting question. There is a 1-pixel attack. Indeed. So you can attack only 1 pixel, but the pixel is like the very important pixel. Then you can fool the video. And you can choose in this case, your epsilon could be a little bit larger because only 1 pixel attack. So that many interesting research around. It's like 2018, 19. It's one of the best paper award in the CVPR or NeurIPS, one of them. And afterwards, people working on it. And right now, it's like the computer scientist finding another idea to, attack video or attack image and defense video, defense image. And then these days, I found that people using the vision transformer, and they just using the vision transformer and then making an attack over the vision transformer. So that is also very interesting direction. So the takeaways are adversarial defense and attack is important issue in real world. And secondly, we can introduce numerical algorithm that we can help to defend against that kind of the adversarial attack. And also finding vulnerable frame is very important for the video attack. And also adversarial attack and defense still widely open. I said that the accuracy over the attack is still 60%-ish. So we have to increase the number of the accuracy. So there are many things to be done. Okay, so that is first part. So I just study some of the computer vision problem by using the mathematical idea. The second part is just in between, like is get together for the machine learning and numerical methods all together. So in that case, I just choose the topic for the material science and the optimal device design. So when I work on the numerical PDE, one of my subjects is layered medium scattering. So thinking about the electromagnetic waves. And we have a stack of the layers, layered medium, and then these are nano structure, very thin materials like the 10 nanometer, 15 nanometer, that kind of very thin nanometer, and then we can think about the periodic the domain. And that kind of the layered medium example is very important for the seismic image and underwater acoustics. But mostly importantly, I thinking about the plasmonic nanostructure for the solar cell example, that kind of thing. I'm very much interested in that kind of example. So that is the example for the layered medium scattering. So you can see it's 1 micron, and 1 micron is 1,000 nanometer. So it's one of the stack is very small size. It's like the 50 nanometer or something like that. And this is kind of flat interface, but you can think about the corrugation of that kind of the interface. Then corrugation makes, so what is the wavelength of the sunlight? 150 nanometer. And this one is smaller than 150 nanometer. So you can think about the multiple of this 150, the wavelength of the sunlight. Then you can think about the resonance, and you can think about the excitation of that kind of the energy and power density of the solar cell. That is another interesting area for the material science and computational mathematics. So I'm not a physicist. I'm not doing that kind of the physical experiments. I'm the numerical mathematician. So numerical simulation is very much important in this case. Why? Building that kind of nano device is very expensive. And once you build it, you cannot change it. You cannot corrugate. You cannot shift the refractive index of this kind of the materials. But numerical simulation is very cheap, very easy. You can just change the number and then click, then you can run another simulation. So it's very much flexible. So physicists and engineers want to see the numerical simulation before they build that kind of expensive devices. So that is another contribution for what the computational mathematician can do. Okay, so this is a description of the problem. So I'm going to work on the multiply layered structure, and we have a grading, small grading interface between the two material, maybe 3 or 4 materials, and we have a monochromatic wave. It's like the from top to bottom, and also we think about the quasi-periodic boundary condition. And between the material, we think about the transmission boundary condition between them. So that is the basic setting of the problem. And yes, we are going to solve the Maxwell's equation. Of course, it's electromagnetic wave, but permittivity is piecewise constant for each layer because the refractive index is fixed. But permeability is fixed everywhere. It's like the constant everywhere. So in that case, we can just rewrite the Maxwell equation. Then Maxwell equation, we can actually solve it by using the vector Maxwell equation. But we can change the Maxwell equation by using some easy computation, and we can use that kind of the easy Helmholtz equation for each layer. So this is an example of the 3-layer problem. So on the very top layer, you are going to solve the Helmholtz equation, but your wave number is Ku. Second layer, you are going to solve the same Helmholtz equation, but different wave number. Third layer, you are going to solve another Helmholtz equation, but also different wave number. And you have 3 different Helmholtz equations for each layer. And then you are going to think about the interface boundary condition, which is transmission boundary condition, like this way, this guy and that guy. So it's very well-defined problem. So we are going to solve, we can find numerical solution for that. But our interface is not flat. Our interface has a small corrugation because sunlight, 150 nanometer, and we have to think about the maybe multiple of this kind of the wavelengths of sunlight, then we can expect that kind of resonance. So maybe our corrugation is 75 nanometer or 32.5 nanometer, something like that. So in the numerical PD sense, we aim to find higher the numerical solution for that kind of Helmholtz equation over the periodic layered medium. And method is we developed the Hopf method, higher the perturbation of surfaces. I'm not going to dive into the detail for the Hopf method. This is not the numerical PD class. And the numerical discretization, I use the spectral element method, Randall-Galerkin method for that, because we can think about the very high accuracy, because this is nanomaterial. So we need like the 10 to the negative 12, 10 to the negative 14, 15 accuracy for the numerical simulation. Great. So it's like the overview of the Hopf method, but yeah, I'm going to skip it because we are not going to dive into that kind of the numerical method. If you're interested in the Hopf method, just let me know. Then I will send you my paper. And eventually, by using the numerical method, it's like the multi-layered medium. So whatever the number of the layer is, this is 10 to the negative 14, 15, I'm not 16, I'm not sure. So 3 layer, 7 layer, 11 layer, we can reach almost the machine precision by using my numerical method. So our numerical method is very much accurate. So in the sense of the numerical analysis, it's good. So we can do it. But I'm going to think about some application. So we have a very nice numerical solver. I want to use it in actual problem, some real-world application as an applied mathematician. So how can I do that? So this is the solar cell example, so-called solar thermophotovoltaics. It's very hard to pronounce as in Korean. So the meaning of the thermophotovoltaic is, solar cell is not efficient. You can read the newspaper and article. Everybody knows it because there has a theoretical limit. So we introduce like the heat. The thermal photovoltaic means like you are going to introduce the heat energy. So sunlight going down to your solar panel, but you are going to trapping the heat together. And then you also use the wave plus heat together. That's much more efficient than classical solar panel and solar cells. And that Bragg reflector, it's like a stack of the material, titania, silica in that sense, and they can trap the heat energy very well. So that is called the Bragg reflector. Okay, so anyway, I'm going to design that kind of the Bragg reflector in the numerical sense. So this is the actual computational case. So on the top, optically thin vacuum. On the bottom, optically thick, not thin, tungsten. And in the middle, they have alloy, like the Al2O3 and tungsten. And in the middle, you can think of the Bragg reflector, SiO2, TiO2, SiO2, TiO2. It's like a stack. And then you cannot think about the flat interface or the corrugated interface, both of them, and see which one is better. Of course, corrugated one is better because we can think about the resonance. So this red one is emissivity. Red one is emissivity. We have a corrugation. The size is 2050 nanometer. Then you can have some large energy here. But black one is flat interface, H equal to 0. It's magnitude of the sinusoidal, the interface. So black one is like there. So of course, red one is better, the better energy. They can trap the better energy. And then also, this is a graph of the power density and spectral efficiency. You can see some peak of the power density at the like the 2.9 micron. That is kind of the resonance, the resonance wavelength part. So if you can change your period of the interface, which is multiple of the wavelengths of the sunlight, then you can see the resonance. That's the numerical evidence for that. So, okay, I can make that kind of the example by myself. So it's quite successful and very interesting application. But how can we connect this one to the machine learning? So take a looking at the problem setting. Then it's like the stack of the layer, but we have some kind of the library of the material, and each material has a different refractive index. And different refractive index gives the different wave number of the Helmholtz equation. And you can choose the number of the layer. You can choose the thickness of the layer. You can choose what kind of material are you use. Okay, so you have many freedom, a lot of freedom to be, tested. So it's like the, very complicated problem and the optimization problem. So it's like the optimal design of the nanomaterial. It's very interesting part for the nanophotonics and engineering. And we have a very nice numerical solver, and we know how to handle machine learning. So why not? We can just tackle this kind of problem by using the machine learning and our numerical method altogether. So to do that, classical global optimization, the technique is not, meaningful for us. So we just think about the machine learning and deep learning architecture. So this is the variation autoencoder and conditional variation autoencoder. It's developed by the computer vision guy, generative model. So if you think about this kind of the cute dog picture and encoder, you can just think about the latent space, and then you can put a decoder, and then you can reconstruct that dog image. And if you think about the conditioning, then you can condition dog right here, then you can fit your neural network to generate that kind of dog picture, which never seen in your test set or the other kind of the training set. So that is good. So we are going to think about that kind of generative model. But how? It's well developed in 2015, 16 by King Ma. So this is our case. The conditional variation autoencoder to the electromagnetic design. So our input is that kind of thing. So we have number of layer, it's fixed air and silica, but we don't know the thickness of the layer. We don't know what's the refractive index of the layer. So we have a very much different input data, and we can generate 50,000 input data, and we can actually test 50,000 input data by using our numerical simulation. We have a Hopf method, then we have a training set and test set altogether. And we can generate that kind of our variation autoencoder design, we can generate new design of our optical device, which never seen in our test or training set. And if we can put the condition, then we can specifically generate some optical device which satisfies some condition. For example, we are going to increasing emissivity or reflectivity, decreasing reflectivity, increasing emissivity, then decreasing the reflectivity. So we are going to find smallest reflectivity. So after computing the reflectivity by using the numerical method, then we can, our label is reflectivity, our input is the optical device design. So we can generate 50,000 training and test data set, and then train that kind of the variational autoencoder, conditional variational autoencoder. And moreover, by doing this conditioning, we can ask to our decoder to generate, for example, in our test data set and training data set, reflectivity 0.1 is smallest. Then we can put the condition 0.08 or 0.09. Then if we are lucky, they can generate which has a reflectivity smaller than 0.1. And we can actually test our actual reflectivity by using our Hopf numerical method. So we can augment our data set by using this kind of the variational autoencoder. So that is weak sense of the active learning. Of course, active learning, people think about the Bayesian optimization and Gaussian process, but this is weak sense. So we are going to think about some generate random sample, and our variational autoencoder create some selected candidates, and we can measure reflectivity by using our numerical method, which is exact. And if we can have a small reflectivity, then we can add the small reflectivity optical device to our input. So we can augment the design of the new optical device design in this way. So it's like 1,000. So we can generate maybe 2,000 small reflectivity example. Then our variational autoencoder getting more and more powerful. So can we get the nice number here? So the A is like the 2019 New Journal of Physics. So this guy, by using the classical global optimization method, they have a 1.81% the reflectivity in their method. And B, it's like the 2021 nanophotonics. They use the just neural networks, and they have a 1.82% reflectivity. In our active learning, 2022, we have a 1.52, where they have a 0.3 improvement. Yeah, somebody can say it's marginal, but it's our method is very, very cheap. It's very fast. Our variational autoencoder is very fast. Our Hopf method is not very expensive. So our method works. That's, our new findings. So, and then we can also generate some kind of regressor. I'm going to skip it. And one more further application is that the metamaterial. After finishing that project, one of my friends in mechanical engineering, he heard about my project. And can you do the same thing for the metamaterial? So it's like the 3D printing, the metamaterial, and this black part is 0, white part is 1. So it's like the 50 by 50, like the image kind of thing, black and white image. And by using that kind of the metamaterial, this is called the unicell, we can expect some kind of the figure of marriage. For example, the Poisson ratio. Poisson ratio is smaller and smaller, and then if we go down to the negative Poisson ratio, that is new material. So we call this one is metamaterial. How can we build this kind of material by using the unicell? 3D printing can do it. So we can actually make the 3D printing. We can make that kind of device. But what kind of shape is the best for the Poisson ratio? How can we generate the negative Poisson ratio in that case? We can do the variational autoencoder. Actually, we have the vector quantized one here. So which called the VQVA developed by the DeepMind guys. And we use that kind of the VQVA for the high resolution. Then we can successfully generate the new metamaterial, which has a negative Poisson ratio. So that is also very interesting the project for me, because it's like the joint work with engineer and mathematician. So I like that kind of thing. Okay, so what's the takeaway? So computational methods are useful for the material science. And also I developed the Hopf method, which is good. But the ML approach with the Hopf method can outperform some of the existing methods. Not always, I would say. I'm just giving one example. I just say just very nice example and good parts. Of course, there is drawbacks. So that's why I just say outperform some of existing methods. And the many applications is available for the optimal device design, and then metamaterial. And that kind of area is widely open. And people just dive into it. And then, we are ready to study this kind of the new subjects. Okay, so these are my collaborator, computer science, the computer scientist, Hyunwoo Kim and Dave Nichols from Math Department, and Stefan Gray and Namjoon Kim, the mechanical engineering. And actually, I don't know where about the domain knowledge. So these people can help me to how to understand what's the metamaterial and what's the 3D printing, what's this kind of the electromagnetic wave and the adversarial attack. I don't know any of them. I always ask them because it's kind of the process, the collaboration, interdisciplinary collaborations. So yeah, that's kind of another thing. Thanks to my collaborator, and then thanks for the attention.
Thank you so much for the wonderful talk. Are there any questions from the audience? I have one. So I'm wondering, it might be probably a big question, but in your Hop method, is it also applicable for 3D domain?
Sure.
So that, because I was thinking about the example you showed somehow the 2D, shape. But,
yes.
That can be easily extended with we have a like cropped part is uniform over the one face. But I feel like it might be more efficient if we can do some variation on how the corruption rate, the
correlation.
Yeah, the changes over the space. So that, have you considered that kind of extension?
Yeah, we did it actually. Actually, we did the Maxwell equation, vectorial Maxwell equation. But eventually, we find that the 2D reduction of the Maxwell equation is not very different from the Helmholtz equation. So I just showed the Helmholtz equation example, but we also did like the 3D vector, the Maxwell equation. But geometry is much more interesting, as you said. Like for the moment, we can just have that kind of the range of the sigmoidal function, but you can just put some kind of mountain in the middle altogether. That could be much more interesting geometry. But basically, the engineers, when they fabricate the interface, they don't do like the smooth interface. They fabricate like this kind of sawtooth thing. But sawtooth thing, we can do it by using some kind of some approximation technique. So sawtooth is pretty much similar to the smooth profile in terms of the figure of merit. So that's what we find.
Thank you.
Mm-hmm.
You designed the new neural network using an idea from the nanophotonics.
Yes.
So, but for me, it's hard to understand why that kind of new neural network is robust to the adversarial attack. And so, so do you have any intuition or okay? So I think that anybody can design new neural network from this mathematical numerical method. So how do you know that would be good for such adversarial attack?
Yes, that's a very important question, actually. Thanks for asking. So we cannot prove anything, in fact, but my intuition is that, so adversarial attack, that means that we give a perturbation over the initial image. It's kind of the perturbation of the initial condition of the dynamical system. That's what I understand at the beginning. So we have some kind of noise of the initial condition, and we don't want to propagate that kind of noise over the time, discretization. So in that sense, SSP-like method is better because it's TVD. So total variation diminishing. So error doesn't propagate so far in this kind of case. Of course, we don't know this dynamic system is well posed or not, or solution is unique or not. We have no idea about it, but it's just intuition. So starting from mathematical intuition, and we just apply our algorithm to the actual neural network because it's not very complicated and it works. So, and then luckily, my intuition works a little bit well, because look at this. It's like the midpoint RK2. It's not SSP2. So midpoint RK2, it's degraded, the kind of the performance. So that kind of the total variation diminishing helps us, that kind of the PGR small, keep the PGR small. That's why our neural networks do not propagate that kind of noise from the initial condition. So that is my initial understanding, intuition. Of course, I cannot prove that. So that's the main issue for that.
Yeah, from mathematical point of view, okay, so we have a specific operator. X is given as input.
Yes.
So that is propagating by that operator.
That's right.
Okay. So actually the operator is given just when you put a method, the kind of method to find the solutions or the time behavior given by that operator.
That's right. Yes, discretize that.
Yeah, but neural network means we have freedom to decide that operate in each layer and between layers.
That's right.
We're gonna decide the parameters. So it just looks like in shape, it's like the dynamic system, but if you look at it, we're gonna design the parameters. We're gonna decide the parameters. Then we need to decide the parameters to make the final result, which is P to the given data or labeled data. So if you change the network, then totally different parameters that are given. So decision of that parameter, which is in a sense insensitive or robust to the slightly change of initial data. I'm not sure why that kind of thing happens. So, in my opinion, usually the neural network is learned very well the high frequency data. So usually human beings or the numerical method learn very well the low frequency data.
Yes.
And yeah, you are the numerical analyst.
That's right.
We know that the reducing high frequency error is very hard in user numerical method.
Exactly.
My feeling is that the neural network learns high frequency data very quickly, very easily. Okay, so that means, it's sensitive to the adversarial attack using that kind of the texture or noise. I think that's kind of neural properties of neural network. But your neural network is, in a sense, robust to that kind of high frequency, the perturbation. So, yeah. So you applied that to that problems, then it would be better. Yeah. So you may get better results. But for me, still, that is useful to perturbate that kind of adversarial attack. Then I may think that kind of things would be applied to other kind of problems also. Okay. Yeah. Okay. Yeah. That's just my comment.
That's a very interesting comment, and I like it. Thank you very much. And just one quick my thinking. Yeah. So in fact, there is a kind of F principle or spectral bias, that kind of thing. That means that the neural network learns low frequency first, and after learning every low frequency, and they start to learn the high frequency thing. And in this case, adversarial attack, maybe we can understand this one as like some kind of the high frequency noise. But I think this is like nothing to do with the frequency in my understanding, just my understanding. Yeah, because it's just a perturbation over our loss function, gradient direction. So that's why it's like I understand that that kind of the attack is related to our CNN and ResNet function operator. That is my understanding for that. But frankly speaking, I didn't prove anything for that. So that's very sound suggestion and sound comments to me. So I have to sit down there and then think about more about that kind of the adversarial attack, the origin of the adversarial attack. In fact, the new trend for that kind of the committee of the adversarial attack, they don't dive into the Olympics like the 60%, 61%. They just, okay, can we impose that kind of robustness to the neural network itself? And they just going back to the, the initial idea about the adversarial attack. Maybe people misunderstood something, like batch normalization. At the beginning, people thought about that that thing came from the covariance shift, but actually it's not. So that kind of misunderstanding is around also this kind of committee, and that's very interesting and applicable subject. That's why I dive into it. But I'm frankly speaking, I have to understand more about it because I don't think I'm kind of aced it. So that kind of the nice comment and suggestion could be very, very fruitful to me. Thank you so much. Yeah.
Okay, for the interest of time, let's thank to the speaker again for a wonderful talk. Thank you very much. And then we are going to have lunch at the faculty club so that if you are send the email to the speakers, probably, yeah, we'll continue the speakers on the lunch. Yeah. Thank you for attending. Thank you so much.
Thank you.